Oh yeah. Also,
Have
how
I
was
disappeared?
Eddie's lesson? No, no.
I'm still.
You're
Can you still see my video?
yeah, yeah. The yellow shirt. Still see.
Right, that's very interesting. Okay, that's fine. I am not bothered whether you see me or not, really, as long as you can hear me, most importantly.
Yeah,
And now I need to minimize this because we are in full record mode. Yes, so what we've been doing with Eddie, it's really, really been going well. And it's something I said I'll definitely suggest now that you're moving into year 13. So I've been having 2 hour lessons with Eddie. Um,
yeah,
and that's just because, I know that you cover more ground. And at year 13, it's not GCSEs. You're going to have a lot more questions, and the stuff we're dealing with is pretty complex. So it's much better, or you absorb it much easier if it's not just sort of compacted in an hour, so to speak.
yeah,
And you get more times to do exam questions in my presence, which is really good. Then that means that when you go off to do your homework, your confidence is actually on a much better level than if you just have an hour session. And that's partly the reason
yeah,
why I was driving towards that deal, because then of course each lesson will be 2 hour long. That's if you think you can. I'm literally just telling you to say, as a general piece of advice, at year
yeah,
13, everyone I tutor physics wise, I strongly recommend 2 hours, and they find it the most beneficial. So have a
yeah.
think about it, Conrad. I don't want to put you under any pressure of sorts,
Definitely.
but this is the motivation for me telling you this is because it would be beneficial for you more than
Yeah.
it's not monetary at all. It's very much just from the level of amount of learning that you're going to get. So yeah, we've had good sessions. Yesterday, he had to dash off, so we didn't get to the end of it because then he realized he had to get to the airport and do some shopping
Oh
and
yeah.
run off to Muswell Hill and do all sorts. So
Oh gosh,
that was
yeah,
cut short.
literally.
But it's the holidays, so I am very flexible because, of course, chances are I'll possibly be in a similar predicament where all of a sudden, last minute, I realize there's something I've forgotten. So it's holidays. Right,
Yeah.
how have you been keeping? Because obviously you've come back from Rome. Are you feeling refreshed? Are you feeling rejuvenated? You wishing you were still
Yeah.
there? Are you glad to be back? What's the
I
score?
I'm glad to be back and glad I went. It's all nice.
Good.
It was so hot in Rome, I just could not stand it. So yeah, I'm glad to be back.
I can imagine. Good stuff. Good
Yeah.
stuff. Good stuff. Back to cool grey England. Why not? Right. So physics is our business today, as usual. But today it's going to take on a very mathematical twist.
Ooh,
Extremely
fun.
mathematical. You will possibly be thinking you're having a maths lesson, which it has to be because in
Fun,
year
yeah.
13 there's going to be some maths you'd have never encountered at GCSE, and you need to
Yeah.
gain exposure to it. So I realized that, look, if I am going to or if we are going to delve into the year 13 topics, you need this mathematical base. Otherwise
Awesome.
you won't be able to compute everything that's going on.
Yeah, that's really good. Yeah, I definitely
Excellent.
do need to sort of
So
learn
it
more
will be
maths.
very, very mathsy, and I'll take my time with it, and like ask me a lot of
Yeah.
questions. But before that, I'm just going to throw in just a general starter, just to bring to fore some of the stuff we've brought. But it shouldn't hopefully take us too long. So you have a wire of length. Choose a length.
A meter.
1 meter. Good. A wire of length 1 meter, carrying a current of, choose a current,
10 amps.
10 amps. Cool. A wire of length 1 meter, I will say, let's take this and I will say carries a current of 10 amps. What is the total momentum of the electrons? So charge of an electron, 1.6
1.602
tons.
times 10 to the minus
Good.
19.
And the mass of an electron,
9.11 times 10 to the minus 31.
spot on. Well done. You're doing very well. So this is the only information I am providing you with.
Awesome.
I'll be kind enough because I know
Um,
that you have a data sheet, so I will throw in this
yeah,
as
my
well.
data sheet is somewhere around here. was doing physics downstairs earlier, so let me just rush
Yeah, go
downstairs real quick.
for it, Conrad. No rush.
Right, yeah. How did I do this again? Okay, so that's all right.
And we know that momentum is mass times velocity.
Yeah. So I have. Should I do I? I'm doing I equals NEVA.
Okay, good.
Oh,
Well,
right,
I
yeah.
suppose Eddie told me that you guys have been told to remember that I will never.
Yeah, I never, yeah.
I never.
Well,
There we go. Okay, cool.
Yeah, so. Yeah, okay, so. We have 10. I still need to get that the camera, so you can
Don't
see my
worry,
workings out.
don't worry. You're thinking out loud. You're telling me what you're doing. That gives me a bit of a glimpse.
So, yeah. So I'll just rearrange.
Okay.
For V, so I'll just do I over NEA equals V. Do we know the cross-sectional area?
No, all you've been given is just this information. Just this.
Right.
Nothing more.
Momentum. Do we need it? 10 over. So how many in a charge? It's trying to figure out how I can sort of work that out without the cross-sectional area.
Well, there's two things you don't know really here, isn't it, Conrad? You don't know this.
Yeah.
And you don't know that.
Yeah.
Well, neither do you know this.
No. So is quite. Oh wait, can I? Square E equals half mv squared. Q. Can I use the kinetic energy equation to find out V?
The only problem with that is you don't know what kinetic energy these electrons have. But good that you're thinking out widely. You don't know what this value is, so therefore you cannot work this value. If you knew the kinetic energy,
yeah,
then yes, you can work out V. And remember that this formula only works for one electron. For the mass of one electron.
Right.
The question is saying the total momentum
Of electrons, right.
of electrons, of the,
Yeah.
I should have said, of the, and to be more specific, the conducting electrons. Okay? Because the other electrons are not going to be moving. It's the conducting electrons. So that now makes it very much
So
accurate in asking.
So can I need to work out. I can work out n. That's right. Just the number of electrons in 10 amps. Right.
Now, what is n? Can you remind me? What is n? Can you remember n?
The amount of flowing the amount of electrons in amount of electrons in 1 unit charge.
Not quite, but you're so nearly there. You're so nearly there, Conrad. It's number of electrons per meter cubed.
Meter cubed, yeah.
Okay? And A is the area, V is the velocity, E is the charge.
Yeah.
So remember that this is the number of electrons per meter cubed.
Right. So
and this is what we call the number density, isn't it? It's known as the number density. Good.
If I do the reciprocal of 1.6 times 10 to the 19.
Why are you doing the reciprocal of that?
Is that how many isn't that just the number of electrons in a unit of charge?
Not quite. So when you have a conductor,
what is that for me?
So when you have a conductor, there's going to be a certain amount of free electrons in a given volume.
Yeah.
The electrons that conduct. And this here, so we look at the number of electrons in 1 meter cubed. So we take a 1 meter cubed portion and we count the number of electrons in there. And that's how we obtain n.
Yeah.
So if you say 1 divided by 1.6, that would not give you the number of electrons.
No.
In a meter cubed.
Yeah. That's
Do you want us to work through it together?
Definitely confused. Yeah.
You're not to worry. Now I will not beat about the bush. This is extremely difficult. As a problem, extremely difficult, because it's not conventional. There's so many things that are missing that you're not accustomed to seeing them missing when you ask the question on drift velocity or any such thing.
Yeah.
So, but I threw it in for a reason, because I need to throw you at the deep end to help you gain more tricks. So I equals never. That's the equation we're starting off with. Now, you're absolutely right. You arranged the equation and you said V equals I over N. What is it? NAE?
Yeah.
Good. Rearrangement. First step. That's the value for my velocity. I know I know E, I don't know N, I don't know A. And it's already looking problematic. So now my momentum P is given by mass times velocity. So my momentum is given by M multiplied by I over NAE, because that's my velocity of a single electron. So this is the drift velocity of one electron. Okay, so this here, this momentum is the momentum of one electron. Please note, one electron. Do you agree?
Yeah.
Because that's the drift velocity of one electron. This equation gives me the momentum of one electron. So if I want to find the total momentum of all the electrons, surely I need to know, well, I need to multiply the momentum of one electron by the number of electrons that I've got. Are you following so far?
Yeah.
Good. So let me work out the total mass of electrons that I've got. Now the cross-sectional area of this, I'm going to call it A. And of course it's got a length, as you rightly decided, of 1 meter. So that's the length. Now area times length always gives volume. Do you agree with that?
Yeah.
Good. So therefore, if my number density, if I have n electrons per meter cubed in my volume,
I think there's building works going on outside.
they chose the perfect time, didn't they?
Perfect time.
They hacked into your phone. They hacked into your phone and realized.
That's super duper helpful.
Good. So area times length gives us the volume. Now if I've got n number of electrons per meter cubed, what about in an area of A times L? How many will I have? Well, it's the number of electrons per meter cubed multiplied by the volume of my conductor. Are you following so far? Make sure you are. It's absolutely vital. Good. So if I now take the number density and multiply it by the volume, this should give me the number of electrons in the conductor. This should give me the total number of electrons in conductor. Are you following so far?
Yeah.
Good. Which means therefore that if I want to find the total mass, because if I want to find the total momentum, I need to know the total mass.
Yeah.
The velocity is the same for each one of them. I just need to know what the total mass of all the electrons is. So what's the total mass going to be given by? Total electron mass will be given by the total number of electrons multiplied by the mass of one electron. Will be given by NaL multiplied by E. Sorry, ME, I beg your pardon, ME, which is the mass of one electron. ME, sorry, Conrad. Are you following so far? NaL, ME. Good.
No.
So now I'm going to take, come on, can't I scroll further down? I don't want to go to another page. 100% maybe. Oh God, that's not working. Anyway, it doesn't matter. So the total momentum will be given by total mass NaL multiplied by the mass of the electron. This is the total mass multiplied by the velocity, which is this here, I over NaE. Are you following so far?
Yes.
Good. So the two n's cancel out. I don't need to know the number density. The two a's cancel out. I don't need to know the area. So my formula now for the total momentum reduces to length times the mass of the electron times the current divided by the charge of an electron.
Yeah.
And so my final answer is the length is, what did you say? 1 times the mass of an electron is 9.11 times 10 to the minus 31 multiplied by 10 divided by the charge of an electron, 1.6 times 10 to the minus 19. What does that give you as your final answer? Just gonna have to type that in as well. So
61 times 10 over 6. 5.7 times 10 to the minus 11.
5.7 times 10 to the minus 11. Yeah? Or in other words, 0.6 pico Newton second. Okay? 0.6 pico Newton seconds. Or 5.7, as you said, or 6 times 10 to the minus 11. Alright. And that's done. really difficult, very difficult. This is the Cambridge,
it makes
Oxford
sense. I wouldn't
University
have thought
standard
to
question.
sort of do the A times L equals volume thing.
Yeah, but that's okay. The whole point about it is, Conrad, I'm here to give you tricks. This is about exposure. The more things you've seen, on another day you'll see another question that's different from this, but will apply the same way of working. And because you've seen it, you might have that extra thought to say, hang on, how do I tackle this? Okay, good. So now we move into our very exciting topic of logs and exponentials. We're now going maths. Let me just go. All right, there we go. So logs and exponentials. Now you have not covered this. I am aware of that.
Yeah.
But this element of exponentials, this here, you will be a bit familiar with. So what does an exponential look like? So if you have something like y equals to a multiplied by the dot means multiplication, b to the power of x, this is what we call, in other words, a power function. Now notice here that a and b are constants, and y and x are what we call variables. And in effect, x is what we call our input, and y is what we refer to as our output. It's a function. You put something in, you get something out.
Right.
So we're dealing with letters. They don't mean much here. So we'll just try and bring this a little bit more to life that we can relate to. So imagine I have a function that says y is equal to 2 to the power of x. This here is an exponential. Now why is it known as an exponential? Because as the values of x, yes, increase by the same interval, the value of y does not increase by the same intervals. Now you will recall from your GCSE days, I'm just going to make life a little bit easy here, and then you're going to help me fill this table in. So you'd have done something like this if you were given a function and you had to plot it. So we'll start off from -2, -1, and these here of course are my independent or my x values, and down here are my dependent values. 0, 1, 2, 3. I might add a next one there just to drive the point home. So when x is -2, what is y? Can you help me fill this table?
When x is -2, 0.25.
Correct, a quarter. And when x is -1,
I probably should maybe have done that in my head. 0.5.
good. When x is 0,
1.
correct. When x is 1, I'll help you do that one. 2. When x is 2, 4.
4, yeah.
When x is 3,
8.
and when x
What
is
did I just
4,
say? Wait. Yeah. 16.
correct. Now notice how the x values are going up by the same intervals of 1. But as they become larger, the intervals or the gap between the y values is becoming ridiculously big. So here the interval was 1, the interval went up to 2, then the interval went up to 4, then the interval went up to 8. So it's increasing rapidly, and that is what we refer to as an exponential increase. So for the same x interval, as we make x larger, y starts increasing rapidly. Okay? So that is what makes it, as I said, an exponential. If I had to plot this, well, I say plot, but I'll say correctly use the word sketch. There we go, y, and that's my x-axis. This, of course, has an intercept of 1. And we can see that as x becomes more negative, the value of y becomes smaller. Note that this graph will never ever touch the x-axis, so it looks like this. So this is y equals to 2 to the power of x. Now, can you tell me, how do you think the graph of y equals to 3 to the x will look like? Have a think. If I had to sketch it on here, what would it look like? Would it be this, which I'm going to call A? Would it be let's use a different color. Will it be that, which I'm going to call B?
Would it be sort of A?
Correct. It's A. It's getting much bigger at a much quicker rate. So you can see that with x is 1, that is 3 as opposed to 2. So it's a much bigger number. So you are right. Good. Now also another common thing about them is, generally, you can see that when x is 0, they all pass through the coordinate 0, 1.
Yeah, that makes sense.
Yeah? They all pass through that coordinate, as long as they don't have another constant in front.
Yeah.
Can you see here there's only one constant, which is 3, but there are times when you do get equations which say y equals 2 times 3 to the x, in which case, where would a graph like this cross the y-axis? Any ideas? Question is, where would this cut the y-axis? So this we know cuts the y-axis, cuts y-axis at 0, 1. Likewise, this cuts y-axis at 0, 1. Where do you reckon this might cut the axis?
I've got 2, but they could both be wrong. It's either 2 or 4.
Well, actually the answer is 2. Because when any graph cuts the y-axis, the value of x on that function is 0. So whenever you want to find out where a graph cuts the y-axis, simply make x 0 in that function. So if we go here now, we've got y is equal to 2 times 3 to the power of 0. So firstly, you deal with the power. It comes back to BODMAS.
Yeah.
So you deal with the indices first before you multiply. Now 3 to the power of 0, anything raised to the power of 0, a to the power of 0 is always 1. Anything raised to the power of 0 is 1. So 1 times 2 is 2, which means that this cuts the the y-axis at y equals to 2. So if there's a number in front of it, you simply need to multiply that number by 1. If the number is on its own, such as here, then this will always cut at 0, 1. Are you following so far?
Yeah.
Good. So we now understand what these power laws look like. You could also have, before I go into that, I'm just trying to think, should I make you sketch something? No, it's not a maths lesson, it's a physics lesson. I want to get into the nitty-gritty of it. So far, we have looked at power functions, and let's just look at an example of power functions. How are they disguised? What do they look like? So examples of what we call power functions, which you're going to encounter in your physics course. By the way, Conrad, I'm really glad that I don't have to tell you to write things down. You do it naturally, because it's very important. Very good, because you need to be building neurological connections while, you know what I mean, like writing all these things down just makes your work a lot less harder for when you look at it yourself. because you've already done
Yeah.
it and you've been writing it. Very good. Okay, so we have got a formula. Now, I'll just write these in just a general form. Now, this is still very much in the form of y. You know what? Actually, I will use... Yeah, I'll use A. Think about A as representing the y, and think about B as representing the x. And think about this k here as representing a constant. In other words, just a number. Any number. So that's the first power relationship. Then we've got A equals KB squared. Now, of course, yeah, in this particular case, the B is now raised to the power of 2. The other ones that you need to know: A equals K over B, A equals K over B squared, A equals K root of B, and we can have something like A equals minus K root of B. Okay, remember K is the constant. I will quickly give you a reminder of one power function we have met as well, which we're going to talk about later on. Remember this power function we met? Can you remember this?
I think slightly, yeah.
Yeah, what's this formula for?
Oh gosh, just gone.
Don't worry. This is nuclear radius. So this A represents the atomic number, or sorry, rather more specifically the nuclear number, because I don't like that word, mass number, nuclear number. So this is an example of a power function. And these are some of the power functions, or rather when you see equations that look like this, these are what we call power functions. So this is raised to the power of 1, 1, 2. This is raised to the power of minus 1 because this is the same as KB to the power of minus 1. This is the same as KB to the power of minus 2. That's why we call them power functions. Something has been raised to a power. Okay? Likewise, KB to the power of half. And likewise, this is minus KB to the power of minus half. Okay? So these are other forms or representations that I could have written these in. Right. We're taking this slow because, like I say, this is something in A levels. If we were doing A level maths, this would span 3 lessons. So it really would.
Yeah.
It really would. And I know you're not doing A level maths, so I want to make sure that I'm building you up gradually and this stuff doesn't seem unsurmountable. Okay, so now that we've looked at power laws, let's look at what we mean by this mystery of logarithms. So imagine we had something like this and said 5 squared is equal to 25. You happy with that?
Yeah.
Good. I can rewrite this in a strange mathematical way which you are not formally acquainted with. I can rewrite this as log How on earth did I go from there to there? Do you want to try and hazard a guess?
Yeah.
Go on.
It's as if you sort of reverse the outcome to equal the square that you sort of power you sort of.
You're right, and you've noticed the pattern, and this is why I'd rather. No, you're absolutely right. I'd rather you spot patterns because that's what this whole thing is about. And of course, eventually you're going to be a lifelong learner, so I'm not going to be your tutor all the time. So you're gonna have to teach yourself things, and there are certain ways of looking at things. And one of the most fundamental ways is, firstly, is there a pattern? Can I see something that stands out? Good. So there is a 2 here, and you could argue that this 2 is that 2 there. And that 25 here must be that, different color. This 25 is that 25. And this 5 here is this 5.
Yeah.
So this 5 is what we have a name for this. We call this the base. And if we had to voice out, in English, what is written here, we would say log to the base 5 of 25 is 2. That is how we would articulate it in words. Log to the base 5 of 25 is 2. In other words, what this really means is that what number should this be raised to so that I get that number there? So if I gave you, and we're going to have a go at a few exercises, log to the base 3 27. What must that be? Log to the base 3 of 27. What would you say the answer is?
9.
Nearly there.
Oh. 3.
Very good. I know it's confusing,
but,
Conrad, because you've not. Okay, so the answer is 3. Very, very good. In other words, what number must this number be raised to so that I get this number?
Yeah.
And if I do 3 times 3 times 3, I get 27. Likewise here, if I do 5 times 5, I get 25.
Yeah.
So there is something known as, in other words, think about it as a bullying rule. I'll put this in inverted commas because we could get arrested for this. Okay? The bullying rule. So what the bullying rule says is that if I told you that I've got log, so let's write it here, log to the base a of some number b, and the value is c, it means that, or it implies that, b must be equal to a raised to the power of c. Let's make sure we keep that in a nice boxable, bubble writing, whatever you want to call it.
Yeah, that makes sense.
Good.
Got it on.
And you got that captured, yeah?
Yeah.
Awesome. Now, what are we going to do? We are going to do some maths. I'm going to bring out some maths questions for you to just make sure that you are au fait with what's been covered. Now, where is it? Why are you hiding again? There we go. No, it's disappeared. One moment, Conrad. I'm just trying to. Right. Okay. Oh, we're gonna do this. I did open it. I'm just surprised it won't let me. There we go. I'm gonna try and find something something that will give you a good run for your money. We're not doing everything, like I say, it's familiarization. So I am not running it as if I was teaching you A-level maths, but I know that you need this, and the stronger the grounding you have, the better.
Exactly.
Oh dearie. There we go. So we'll do that one. We're gonna do this one. We're gonna do this one, that one. 4 of them.
Right.
And C. Would it be fair for me to give you this one? No, it'd be unfair because you're not doing A-level maths. No, I've got to. These are from a maths textbook, so I've got to be careful which ones I'm throwing at because some of them are definitely not.
Less
you'd never see them.
For me to embarrass myself. Fucking maths. So.
Trying to help you save face here, Conrad.
Exactly. Yeah.
Good. When you're ready, Conrad.
Um, 10. Okay, so A.
Yeah.
3.
Very good. Excellent.
Okay, F.
You could have done A-level maths. There you go. You're breathing through it like a.
as long as that's as hard as it gets.
There we go. No, you're
I'll
doing
have
good.
a
You're doing good.
chance.
You're doing good. You're doing good.
Okay, so to get to would that be a half?
Very good. Look at that, man. You're
Yeah.
spot on. Spot on. Look at that.
How can I get 0.25 to 16? Need to properly think about this now. I'm not allowed to use a calculator, am I?
You can. You absolutely can. You absolutely can.
Would you be allowed to calculate this in the exam, do you think?
Yes, you will. Yes, because all physics exams are calculator based, so
Right.
you should never worry at all.
So -2 for H.
-2 for H.
Yeah.
So okay, so this is log to the quarter. So a quarter, of
Yeah.
course, is log to the power 4 to the power of -1. And I want to get 16. So what should I raise 4 to the -1 to get 16? I have to raise it to -2. You are absolutely spot on, young sir. Thank you very much.
Awesome. Right. So I might try and just do one without calculator, see how far I get.
Yeah, I like it. Like the moves.
Log 1.5 -1 to 9 over 4. Okay, so log 1.5 to the -1.
Are you over on J, are we?
Yeah.
Good.
To 2.25. Right. Is it just 5 and 1.5? No, okay, that's probably over.
This is a difficult one, and it's not fair to throw it to somebody who's not doing A-level maths. It's a difficult one. Sorry. But
I was going to say -2.
Oh, what did you say? What did you say? Go on, you're doing it. Go on. What did you say? Just say.
I was going to say -2.
Spot. Oh, look at that, man. You're absolutely firing away. I don't even know why I'm.
I initially thought, okay, I should just say -2.
No, you're spot on, because we're saying if you've got 2 over 3, what should you raise it to so you get 9 over 4? Well, I can see from here that if I square this, I'm gonna 2 over 3 all squared gives me 4 over 9. Right. So if I want to get the inverse, well, then this has to be negated.
Right. Yeah, that makes sense. Yeah.
Very good.
That makes if you swear.
Good. Very good. Next, B and C.
B and C.
What should the value of x be?
Let's see. So for B, would that be 9? And for, is that just 7?
You're very bright. There you go, Conrad. Spot on. Good. Excellent.
Okay.
Very good. Very, very
not
good.
Bad, not bad.
Really not bad. Really not bad. It's showing me that you understand the idea, the concept of a log. Good. Next, now that you've understood that, we're going to look at the laws of logarithms. Okay? The laws.
Yeah.
A few more laws for you to learn about. Laws of logs, we're going to call it.
Logs.
So what is the laws, or at least what are some of these laws? The first law states that if you've got log of a times b, you can express this as log a plus log b. Make sure you capture that down.
Yeah.
And this is a multiplication sign, it's not an addition sign.
Yeah.
Good. What's the next law? The next law states that if I've got log a divided by b, then this is the same as log a minus log b. Now, can I just make a quick little point? You have noticed that logs can be expressed to a variety of bases. So I can have log to the base 10 of 5, I could have log to the base 5 of 5, I could have log to the base 2. You've seen that this base can change. You're aware of that, yeah? So here, when we split them, please note that the log will always be the same. Whenever you see a log number not specified at the bottom, Conrad, so here I've not put what base it is, assume that it is to base 10.
Okay, so...
Alright, so I'll put that little note there. Whenever a number is missing as a subscript, not the number in front of the log, but the number as a little subscript. I'll say whenever the base, because that number is called the base. So we'll say here,
why?
It's just out of just convention. So we don't. So on your calculator, you see it says there's a button that says log. We're going to be using that extensively. I don't know if you can see it on my screen.
I can see, yeah.
Yeah? So that button is in log of base 10, but they've not specified the 10 next to it.
Yeah.
So you just have to know it. So whenever log is not expressed with a base, assume it is in base 10. Okay, good. Now, what's the other law? Now, why are these laws important? Because later on, you're going to meet some complex equations, Conrad, I'm afraid to say, and you're going to have to map them onto y equals mx plus c. So you need to understand how to manipulate those complex equations that are going to be thrown your way. Unfortunately, they will have logs. They will look very nasty. They will not look like the equations you've been looking at in year 12.
It's fine.
Absolutely.
We can definitely do it.
Good. That's the spirit.
Yeah. It's the only spirit I can really have, to be honest.
Excellent.
Let's do it.
That's the one.
Yeah.
So if you got log a to the power of b, this is the same as b log a. So the b has come down here. Yeah.
Yeah.
And just a few standard logs you need to know. Log to the base a of a is log to the base a of a is 1. You already spotted that, didn't you?
Yeah.
Yeah, because you answered a question like that. Log to any base of 1 is 0. So these are worth remembering. They can be quite useful. So now that we've looked at that, or these rules now, Conrad, we're gonna have to apply them. Yeah, we're going to have to apply them. So let's look at an equation such as, if you had an equation which said, we're going to look at one of the power laws that we looked at. A equals K times B, which has been raised to some power n. And remember, n can be 1, 2, okay? N can be 1, 2, 3, etc. It can even be a fraction.
Yeah.
Even a fraction. All right? So if we apply the laws of logs to this, we can take logs on both sides. So I'll take logs of A. Log A is equal to log of K times b to the power of n. Why am I taking logs on both sides? Because it's an equation. As long as what I do on one side is replicated on the other side of the equation, in my case the right hand side, then I've not violated any equation rules. The equation remains unchanged. That is why I took logs on the left hand side and I've taken logs on the right hand side. So far so good.
Yeah.
Excellent. Now I can use the laws of logs to dismantle this. Now what does the laws of log say? It says when you're multiplying two things, you can split them apart. So in which case, my right hand side can be expressed as log k plus log b to the n. Are you following? I've applied the first law.
Yeah.
Now I can apply the third law. I'll number these. 1, 2, 3. So this is by application of first law. I can then simplify this using the third law, which now would give me log k plus n log b. And I'm using the second law.
Isn't that the third one?
Third, thank you, sorry. Third.
No problemo.
It's been a long day. You know, I got up at 5:30 today and I had to make I was making mark schemes for all the Cambridge entrance exams because obviously Cambridge, as funny as they'll always be, they never show you the workings. They'll tell you like, okay, the answer is A, the answer there is G, the answer there is F, but getting there, you need to know how to get there. So because I coordinate all these Cambridge exams and whatever, I need to make the mark schemes, but I try and do it in the holidays because then I'm calm and I can just literally give them 3-4 different ways of solving those problems. So I had to do 67 pages of mind-racking Cambridge University entrance exam questions. Yeah, but I survived it. You'll be glad to know. So not a lot of damage done to the brain, fortunately.
Proper work. Like that's like.
It was a workout. No, seriously, it was.
Getting on with it.
It was a workout because by the time I got to like 9 o'clock, and there was this logs problem that they threw in there. I was just like, Cambridge, why do you have to do this? And it's one where, because obviously the questions are all non-calculator for the Cambridge entrance exams.
Yeah.
Actually, I'll share it with you. It was ridiculous, and it just got me thinking, what are you doing? Basically, as simple as it is, it says find the average of log to the base 10 of 27 and log to the base 10 of 64 and log to the base 10 of 216 without a calculator, but find it as a nice. I know. So this one really got me thinking. I spent about 4 minutes, and those questions you're only given like 2 minutes to come up with an answer. So I was thinking this is an unfair question, but we got there in the end. But I'm not going to give you this. Don't not worry. I will not be so harsh as to tell you to find the average of these 3 logs. Okay, right. So this is the main. So these are the 3 laws of logs. So how can we use them? So let's just take this equation now. So we've got log A equals log K plus n log B. Are you following so far?
Yeah.
Good. I'll go to the next page. So we have, if this decides to play ball, log A equals
log brackets K times B have n.
Log K, thank you so much. And it's B and it's log. Hang on, sorry, what was the last? Gosh.
So before the addition.
N log B. N log B. Sorry.
Yeah.
That's the one. Sorry, thanks. All right, cool. N log B. Cool. Now we can see that we have something that generally, if we look at this equation, A equals K times B to the N, A equals K times B to the N. We know that if we had to plot A as our Y on our Y-axis and we plot B on our X-axis, you know, Conrad, we have convinced ourselves that this would look like this. And we know that the intercept here, Conrad, what would the intercept be? Go on, tell me what the intercept would be.
Wouldn't it just be 1? But
No.
Where K.
Thank you, K, because there's a something in front of the B. Good.
Yeah, I was going to say
it was
1 multiplied by K. But
very good. You're following me. That's what I want. Absolutely. You got yourself buckled in there. Super. Right. So that is K. So it's not a straight line. But now that I've used logs, hey, guess what? This now looks like Y equals mx plus c. How on earth does this thing we've done look like this? Well, this time around now, if I plot log of A on this side and I plot log of B on this side, I'm now plotting using logs. Guess what will come out of the wash? A straight line. And what is the intercept of that straight line going to be? Well, if I look at this mapping, remember what we said? At the x-axis I've got log B, it's mapping. Yes?
Yeah.
On my y-axis I've got log A, we're mapping. So what would my intercept be represented by? Conrad, have a go.
Let me just finish mapping all the...
Yeah, go for it, and I'll let you give me your answer once you've had a think.
Would it be log K?
You're flying. I don't know why you never did A-level maths. You're absolutely flying.
I thought... I actually
Absolutely
don't know why
flying.
I did do...
No, but you've got a logical brain. You literally... Like, I've taught this lesson to people doing A-level maths, and they do a lot more... Well, they do not perform at the same level that you are performing at. Let me put it that way.
Well, that's good to know.
And they're doing A-level maths, and they still manage to get B's and whatever. And I'm thinking, yeah, but at least it gives me peace of mind to know that you're going to be good at it. Okay, so I'm not worried. Like, you're not going to find logs tricky. I am definitely convinced now, 100% convinced, because you are performing at Trojan levels. Right, there we go. So that would be log K. Now I'm going to ask you a bit of a difficult one. What would the gradient of this line be?
Would it be n?
Spot on. There we go. You're flying again. Yeah?
Right.
So the gradient here, m, would be equal to n. Very, very good. And this is why I'm saying in the future, well, future, I make it look like it's going to be the next 20, 30 years, in the very impending months that are so nigh and so near, I couldn't really elaborate how close they are. You are going to be faced with things that look like this, and you're going to have to turn them into straight line equations, find what the intercept is, find what n is, and then evaluate what k is. Now, I think we've done enough for today. We've gone through all the laws. We understand how to manipulate them, and we've understood how to turn power equations or power functions into straight line equations.
Yeah.
So now, I have a question for you.
Let's go.
This equation we spoke about before.
Yeah.
Think about how you could use logs on an equation like this so you get a straight line. That's your homework, because you know that this equation, how does it look like? We know how it looks like, yeah? So we have r on one side and we have a there. We know that this thing looks like this because you had that as a multiple choice question.
Exactly, yeah.
Okay? But we know this is not what we want. We want to transform it into a straight line equation. So I want you to think, what would you do? What would you plot so you can get a straight line equation?
Yeah.
Do you want
Just
that
one
as a homework
question.
problem or?
For the RO, is that what does the O
So
represent here?
R naught, this here, don't
R0.
worry, is a
Is that just a
constant.
single
That's a
thing?
constant. That's just a
Yeah.
number,
Okay.
and it's
Okay.
approximately 1 femtometer, which is 1 times 10 to the 15 to the minus 15. I beg your pardon, meters. Normally you have to calculate it, so please do not.
Yeah.
So if you remember, we did some questions. Now just cast your memory back to what we have done, and you see questions like this where we have had to calculate it. Not more than 2-3 lessons ago. You should have something
I
in
need to
there
see the.
with this. Okay.
Yeah.
So should I
Yeah.
leave this here as a homework problem? Now I'll
Yeah.
just write it here and say
If I was. Yeah.
what logs would you plot to obtain a straight line? And I want you to tell me what the intercept means, what is represented by the intercept, what is represented by the gradient once you have established what you're doing. Is that okay?
That is okay.
Super. Right. In which case then, young soldier, we have definitely come to the end of our march, and I shall leave you to your devices. But of course, I shall be sending you the board work, and I shall be sending you some maths questions. So it's not
a
physics.
lot of algebra.
Yeah, there's going to be quite a
I
bit of
don't think I
algebra.
wrote down a single number that whole lesson. It's bad when maths just stops involving numbers.
I know it's very, very
There's
bad.
more writing than
Tell
write
me
my
about it,
philosophy
Conrad.
homework.
I know it's absolutely diabolical at the moment. But look, once we have come out through this, come out to the end of this, your friends who are not doing A-level physics, sorry, A-level maths, they're gonna have to learn this at some point next term or even closer to December, and you have done the right thing. You would have already gone through this, and now at least there's, just to give you a bit of a realistic picture, we are halfway through this.
Oh wow.
Yeah, I know. Like I told you, Conrad, it takes 3-4 lessons teaching to A-level maths students just to get through this, and even those who are not doing A-level maths, for those physicists, you need to cover this over 4 or 5 lessons.
So we've definitely got enough time.
Yeah, so that's what I mean. Like, you've done really well. Like, we have gone, we are now halfway. So next lesson, we're finishing this off, and then we shall be bringing out all those physics questions and exam questions. I said you need to now familiarize yourself. Then we're going to apply this in an exam context.
Awesome.
Okay, so I just want to get the basics, get confident, because the physics part of it, when they do ask you questions, they can be quite diabolical, so I want to make sure you're strong on it.
Awesome.
Superb. Really good. Any questions then for me, young sir?
No, I feel like I definitely got an understanding throughout the whole thing. Like,
good.
You explained it super, super well.
Oh, awesome. Thanks for that, Conrad. I appreciate that feedback there. Good. So all I'm going to do then is I'll send you exam questions, textbook questions with the answers.
Yes.
And then also what I realized, Conrad, I did not send you the answers to last lesson's homework. I apologize.
Oh, right,
I'll send that as well. So this was the stuff on particle physics. So you might want to mark it, because I know we didn't accommodate that in this lesson. For obvious reasons, but yes, have a got marking the work I sent for the homework last time, and I'm only just going to give you the maths questions, but I'll give you the mark schemes, the answers to that. Is that okay?
That is right. Yeah.
Brilliant. Awesome. Any ideas about next lesson?
I feel like it will. Yeah. I mean, I don't know what day. I do definitely one next week. I'm busy on Monday.
Cool.
I feel like any sort of weekday next week.
Yeah, I'm away from Thursday. I'm going to Rotterdam, and then I'm going to Holland for a bit. So.
Oh wow.
Yeah. So,
I can
but not for
at
long,
least
not for
see
long. So from Thursday, and then I'll be back Tuesday. No, I'm meeting up with my old Cambridge mates. Like, we've not met each other for like 9 years. I mean, we're really close. We still talk
wow,
on the phone and everything, but it's been at least 9 years we've not
that'd be
actually all
really
been.
nice.
It will be awesome. And one of them's got
That's
a
right.
yacht, so they said we're gonna have spend a little time on a yacht. And I've not been on a yacht in a long time. I think
Very,
last time I
very.
was on a yacht was when I was 14 or something. So it's been a long time. Yes, I think. So yeah,
That's
I'll
the
be
most
away.
Cambridge story I've heard. It's
Oh
got to be
God,
the
man,
most
they
Cambridge
they are all
story.
crazy. I just hope like when I was back in Cambridge with them, I used to be the one mostly nursing them and looking after them, and we used to go traveling, just like what you're doing with your mates. Like we used to go to
Yeah.
Italy. We used to go like every summer holiday because
Well, that's what
obviously.
I was doing with Eddie. He got us lost, so I was like, I thought I was going to be relaxing. So I was like, I took the phone from him. Oh no, we're not going to Cuba, Eddie. We're going to, the airport. I don't know why you put that in on Google Maps. So I just like we got an hour to our flight. So I just take it from him. We're like, right, just get on that bus.
There's look, Conrad. There's always one in the group, and also that you will find that the more brainier they are and sharper they are, there's certain little things that they find very tricky to do, like read a map or know where they're going. So
Yeah.
like being brainy and smart is not the full package. It's not all of it.
I thought they did teach bearings in
Yeah.
math, but
Look, like if you give them a bearings question, they'll get 10 out of 10.
Exactly.
You know that. Give them a
you
map
should
and say,
test
right,
Eddie on
find
his.
your
I
way.
can
They'll be
now
like,
ask you to test Eddie on his subject. So next time you can test one bearing question to see what I mean.
Exactly. Try that. But
Awesome.
yeah,
I
so
think
I'll be happy, Conrad, if it does help to do a 2-hour session with you anytime between Monday and Wednesday. But
awesome.
think about it. Talk to your folks.
Yeah,
just
I'll
stay in
talk to my
touch.
folks about it.
Awesome.
Yeah, that's either Tuesday or Wednesday. We'll see which one's best for you
I'll
then.
I'll put that on the board
Big
then.
out
So
weekend.
Tuesday/Wed. Next
Awesome.
lesson. Superb. Well,
Right.
enjoy the rest of the sun because I can still see that you got some sunshine peering through your window.
Yeah.
And I'll do all the necessary things I need to do on my part, Conrad.
Awesome.
And of course, I know that you'll be doing the same. So I'll see you on Tuesday, if not Wednesday, and have an awesome time.
Yeah, brilliant.
Salute.
Have a good one.
Cheers. Nice one, Conrad. See you soon. Ta-da.
Yeah.
Bye now.